Namaste and welcome to this lecture on linear algebra through geometry. In the last lecture by Professor Krishna Kumar, you would have seen like what are the different types of solutions that you have for a system of equations. And when you are given a system of linear equations, you actually and you say that you solve for the unknowns, you would have got a feel for what is it to solve the system of equations, which is basically finding the unknowns, or which will basically make the left hand side of each equation equal to the right hand side of the corresponding equations, and the solution simultaneously fixes all the left hand side to be equal to the right hand side. It is that set of values which is going to simultaneously solve the equations that you already have. And we've if you had seen in the last lecture, you would have seen a lot of examples where in which you had this lines, say look at 2x1 plus x2 is equal to 3. This was a line that we had, and then x1 plus 2x2 is equal to 3, and you understood from the last lecture that if you look at the geometry of these two equations, these two are basically lines, straight lines. These are lines which intersect at 1 comma 1, which intersect at 1 comma 1, x1 is equal to 1 and x2 is equal to 1. This was what we had, I mean what you saw in the last lecture, right. And there was also another question in the last lecture where we said, like, do always do the lines always intersect at one point, and probably you looked at a second example where you said 2x1 plus x2 is equal to 3, and you took this example 4x1 plus 2x2 is equal to 6. We had this, and when you looked at the geometry of these two lines were like overlapping, lines overlap, and when we said lines overlap, whatever point x1 comma x2 that was on the line 2x1 plus x2 is equal to 3, you found all those points to lie on 4x1 plus 2x2 is equal to 6 also. Therefore, we said that look, this system of equations, basically you had something to comment about the solutions. You said that look, this has infinitely many number of solutions, infinitely many solutions, right. And this we said the lines intersected only at 1 comma 1, and therefore we said that okay fine, that had a unique solution. And you also had another question which came up during his discussion, which said, look, do lines always have to intersect at one point, or do lines always have to intersect at infinitely many number of points? Can the line not intersect at all? And that is exactly where you had this third example, if I am not wrong, you had this third example which said 2x1 plus x2 is equal to 3, and you had 2x1 plus x2 is equal to 8. And here you found that the lines were parallel, the lines are parallel, and we said that we interpreted the solution to this system of linear equations as basically the point of intersection of the two lines, and in the first case we had the two lines to intersect at 1 comma 1, and we also said that this point 1 comma 1 lies on both the lines, like 2x1 plus x2 is equal to 3 as well as x1 plus x2 is equal to 3, it lies on both the lines, and therefore that became the solution. In the second case we had every point on 2x1 plus x2 is equal to 3 also lies on 4x1 plus 2x2 is equal to 6, which means actually if you see both lines are multiples of, I mean the second line or the second equation is 2 times the first equation, basically it is the same line but just multiplied by 2. So we found that every point on the first line is also there on the second line, and therefore you said we had infinitely many solutions. In the third case that we look at, we have lines to be parallel, which means the lines do not intersect, and we interpreted this case as a system of equations with no solutions at all. Right? We discussed this as system of equations with no solutions. Now what we want to do is, let us pay a little bit more attention to all the system of equations that we have. In fact, first of all what we will do is we will just pay attention to this guy, 2x1 plus x2 is equal to 3 and x1 plus x2 2x2 is equal to 3. So let us look at that example first of all and try to understand what we are trying, what is it when we say solve, and how does the structure of the equation even look like. If we are able to understand the structure of the linear equations that we have in the system, then I think we will be able to make a small headway towards solving the system of equations, and that is more important. So what we will do is, let us look at this, say let us look at this equation 2x1 plus x2 is equal to 3, x1 plus 2x2 is equal to 3. Now compare this equation and what we said, the solution to this system of equation, the solution to this was, or the solution to this equation is x1 is equal to 1, x2 is equal to 1, right. Now there comes the interesting part of it. What is that? Let us look at this, x1 is equal to 1 and x2 is equal to 1, even that represents a system of linear equations, is it not? We have 1x1 plus 0x2 is equal to 1 and we have 0x1 plus 1x2 is equal to 1, and straight away you were able to get the values of, you were able to get the value of x1 to be equal to 1 and x2 is equal to 1. Now how does this geometrically look like? If you look at this system of equation where we have x1 is equal to 1 and x2 is equal to 1, it is pretty interesting because the geometry of this system of equation is simple and straightforward. What is that? We had our 1 2 3 4 along the x1 axis, along the x2 axis, again let us mark 1 2 3 4. So we have this. Now what does the solution do? How does the solution look? That is interesting because it says x1 is equal to 1, x1 is equal to 1 is basically a line parallel to your y axis or x2 axis, right. x1 is equal to 1 is a line parallel to the x2 axis, and if you see x2 is equal to 1, this is basically a line parallel to the x1 axis, and where do they intersect? They intersect exactly at that point which was actually the solution to this system of equation. This is also equal to 1 comma 1. Now what is the difference between this system of equations and the solution that we have? What is this? In fact, if you look at both the pairs of equations like this one and that one, the solution is x1 is equal to 1, x2 is equal to 1, but what is the difference that we have in the structure of these equations? Now that is something which we need to look into. If you look at this example 2x1 plus x2 is equal to 3, there is something interesting that happens. There are two variables here and the two variables seem to be contributing towards the right hand side, and here what we have, the two variables again in the second equation we have x1 plus 2x2 and both of them are actually contributing to the right hand side that you have. Whereas if you look at this pair of equations that we have, x1 plus x2 is equal to, x1 is equal to 1, x2 is equal to 1, it is pretty interesting that there is only one variable in the first equation from which directly I can get the value of the variable, and you have the second variable which is there in the second equation which is x2 is equal to 1, directly I will get the value of x2. I do not really have two equations which will involve both the variables here. So what we have is, if to certain extent we can say that when you have Ax equal to b where every equation is going to have all the variables to be contributing, you call that to be some kind of a coupled system. A coupled system. Now what do we mean by that? All the variables are like coupled, tightly coupled, so that each piece is going to contribute to solving the puzzle. Whereas if you look at the next one, x1 is equal to 1 and x2 is equal to 1, when I say x1 is equal to 1, I see that x2 gets multiplied by 0, the coefficient of x2 is 0 here, and therefore any value of x2 you put, that is not going to matter at all, and therefore you see that x1 is equal to 1 is basically a line which is parallel to your x2 axis, which is this. Similarly, you look at the second equation here, which says x2 is equal to 1. In that case we get our x1 to be any value irrespective of I mean you do not have any kind of restriction on the value of x1, because the value of x1 is going to get multiplied by the coefficient 0. Now what is the difference? If you look at this system where I have x1 is equal to 1, x2 is equal to 1, this corresponds to some kind of a decoupled system. That means you have one equation that, if you look at that first equation, you directly get the value of, let us say, that variable x1. You have x2 which is the second equation, and in the second equation only one variable is involved and you directly get the value of that. So what essentially that we are trying, what we are trying to do is, when we say 2x1 plus x2 is equal to 3 and x1 plus 2x2 is equal to 3, we know the lines are going to be something like this. Let me draw those lines in the same graph that I have here. We have already seen this. It is basically 0 comma 3 and 1.5 comma 0. So I am going to have my L1 line to be this. Suppose if I call this as L1, this line is going to be L1, and if I take the second one is going to be this. Let me take the second one, x1 is equal to 3 when x2 is 0, and x1 is equal to 1.5 and x2 is equal to 1.5 and x1 is equal to 0. So this line is going to be like this. Essentially what we are trying to do is, we have these two lines which are basically oblique to the reference axis, in the sense they make certain angle. Now what we are trying to do is, we are trying to get a system wherein which the lines that you have are aligned parallel to the reference axis. So the question naturally that we have is, when we try to solve a system of equation, the question that we have is, can we move from this system of coupled variables to this system of, let us say, decoupled equations, right. This is something like a decoupled system, because every equation has only one variable, and you take that variable, you actually equate to the right hand side, you get the value of that variable. It is easy to solve. So our goal when we try to solve the system of equation is try to go closer to this system of equations, move from here to a system wherein which we have, let us say, d1 x1 is equal to k1, d1 not equal to 0, d2 x2 is equal to k2, d2 not equal to 0, and so on, in which case the lines will turn out to be parallel to the reference axis. That means you basically want lines which are parallel to x axis, parallel to the reference axis. And it is interesting, you will see at in a later lecture that such system of equations wherein which the solution space is same, you call them to be the equivalent systems, right. Now so what did we say? If we want to solve the system of equations, I need every equation has contribution from both the variables, and therefore it corresponds to giving you one piece of puzzle, and you need both the pieces of puzzles to solve the system of equations. That is what we said. Now let us go back to the next example that we took, where in the case of that infinitely many solutions, where we had 2x1 plus x2 is equal to 3, 4x1 plus 2x2 is equal to 6. We had this system of equations, and in this case what we said is, look, this has infinitely many solutions, infinitely many solutions, we said that. Now what do we mean by that? Let us look at it a minute. So we say x1, value of x1 and x2, you put x1 is equal to 1, x2 is equal to 1, that is a solution. You put x1 is equal to 1.5, x2 is equal to 0, that is a solution. You put x2 is equal to 1.5, sorry, x2 is equal to 3, x1 is equal to 0, that is a solution. You see a whole lot of stuff, x1 is equal to 2 and x2 is equal to -1, and goes on, right. These are all the solutions. Now how did we even arrive at a situation where I was trying to solve a system of equations to get one pair of numbers x1 x2, but now I ended up in a situation where I have infinitely many. This is going to be like a problem of plenty. Every fellow that I have listed here is going to be a solution to the system of equations. Now how did we arrive at such a situation? That is something very interesting, that is something which we need to know, right. How did we get that? You very clearly see that when you have 2x1, if you look at these two equations, that I mean, as I said, it is very clearly seen that this equation is basically 2 times the first equation, which said 2x1 plus x2 is equal to 3. Essentially the lines are the same, right. So what I do is I now try to do this. So I take x1, so I can always do this. I can write x1 is equal to 3 minus x2 the whole by 2, 3 minus x2 whole by 2, or if you want to write the other way around, I can write x2 is equal to 3 minus 2 x1. Now what is interesting here? If you look at what is interesting here, you see that x2 is easily represented by another x2 basically can be expressed in the form of x1 itself. Whereas if you look at the previous example, if I say in the first equation I have x2 is equal to 3 minus 2 x1, in the second equation it is not the case. In the second equation x2 is going to be 3 minus x1 by 2. So these two are not the same, right. Whereas in this example that we see here, these two are, let us say these two are not the same, this and this guy, these two are not the same. Whereas in the second example that we have, in the first equation, from the first equation if you take, you get 2x1 is, I mean x2 is equal to 3 minus 2x1, and you look at the second equation, you are going to get 4 I mean you get 2x2 is equal to 6 minus 4x1, and which again says x2 is equal to 3 minus 2x1. Now what does that mean? That is interesting. What does that mean? That means whatever information that you have, I mean if you look at this, the information that x2 conveys is already captured by x1 itself. Can we say that? Because x2 is expressed in terms of x1, we say that the information conveyed by, let us say, x1 or whatever information that is being conveyed by x2 is actually captured by the information that is conveyed by x1 itself. That means we have some kind of redundant information here, you have some redundant data here, I mean which is very evident from here, because the second equation is a redundant form of the first one. So you have some kind of redundancy here. You have redundancy, that means one variable, one unknown, I mean I am just talking about the 2 by 2 system of equations, or I am going to look at system of linear equations in 2 linear equations in 2 unknowns. So what we see is one unknown is completely specified by the other. That means the second equation is not even, I mean the second equation is the same as the first equation, that means a redundant information is there. Is that clear? There is some kind of redundancy that we have, and this redundancy is what manifests itself as infinitely many solutions. In fact we will get to another way of interpreting this in a couple of minutes from now. Let us go to the third one and see third example, like what happens, and then get back to these guys and see like okay, let us try to interpret it again. Is that clear? We will have one more perspective to the system of equations. Now let us look at the third example. I am quite sure you had also had studied about the idea of inconsistent and consistent systems, which Professor Krishna Kumar has already done, saying that okay, whenever you have a system of linear equations to have a solution, be it unique or infinitely many, you call that system to be a consistent system, and whenever the system does not have a solution, you said that this system is going to be an inconsistent system. I mean, how did that inconsistency manifest? We just saw that the inconsistency arose because we could have a possible measurement error. How did we get to that? We said that okay, I have 2x1 plus x2 is equal to 3. This was the third example from your previous class. 2x1 plus x2 is equal to 3, and we had 2x1 plus x2 is equal to 8. Now what we understand here is both the equations have the left hand side to be the same and the right hand sides they differ. It is like saying I take two quantities of x1 and a quantity of x2 and I measure, let us say, total 3 quantities now, and then I take the same 2 quantities of x1 and the same 1 quantity of x2, and together I am going to measure 8, and that is something which is putting a doubt in our mind whether both of them can be simultaneously correct. That cannot happen because it is the same x1, it is the same 2 quantities that you are taking, it is the same x2, the same 1 quantity that you are taking, you are just going to, it is like saying I have 2 kgs of, let us say, something some x1 and 1 kg of, say, some x2, together the total weight is going to be 3 kg, and then I say 2 kg of x1, again I take 1 kg of x2 and I am going to measure 8 kgs, and how does that happen? How can that happen? So what we say is that is exactly where this inconsistency has set in. There could be some measurement error which could have got you an 8 on one side or 3 on one side, which means what we are going to say is like both the equations cannot be true at the same time. Only one of the equations is going to be true at a particular point of time. You cannot have both of them to be simultaneously true because there is some problem there. The left hand side being the same, the right hand side has to be the same, instead we have the right hand side to be different, and this is exactly what we call as inconsistency or measurement error. So whenever you have something like a measurement error, you will have no solution. Right. Now let us take one more interpretation, that is where this gets even more interesting. Now suppose I tell you, look, this is I just tell you in the 2 dimension that we have, like in the xy plane, you choose any point x1 comma y1 or x1 comma x2. So we say choose arbitrarily choose arbitrarily. How many options do we have? I can choose x1 to be any value, I can choose x2 to be any value, which means in a sense I have no restrictions on x1 or x2. I can choose any value, any real number that I want. There is no constraint, there is no restriction on the set of values that x1 and x2 can assume, which means this is equivalent to saying I have 2 degrees of freedom. Which means if you take the 2 dimensional plane, x1 x2 can be here, 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 anywhere. It can be anywhere in the xy plane. That means I have no restriction, I can play around in the entire 2D plane. I can go take any point that I want, I can fix any x1 comma x2 that I want. There is no restriction at all, which means I have 2 degrees of freedom. That means I am free to choose both the values, right. Apni marzi, I can choose the values. Now the problem comes when I say 2x1 plus x2 is equal to 3, Now what I have x2 is equal to 3 minus 2 x1. Now in this case again I tell you, look, you choose x1, you choose arbitrary values, but there is something interesting here. I do not tell you, you choose arbitrary values x1 and x2 even if I say it does not make sense, because the moment I choose my x1 the x2 value gets fixed, because there is a relation between x1 and x2. Is that right? Here there was no restriction, in this case no restriction at all. No restriction. Here what happens? I can only choose x1 or x2 arbitrarily, because the moment I choose x1 or x2 the other value which is x2 or x1 it gets fixed, because there is a relation between these two guys. So in this case we can choose only one of x1, only one of x1 or x2 arbitrarily. Having chosen, let us say having chosen x1, having chosen x1 value, a value for x1, the value of x2 gets fixed automatically. Right, it gets fixed automatically. And now what we are going to say is, look, this equation that we have has only one degree of freedom. This has one degree of freedom. I can choose only x1 or I can choose only x2. The other fellow, there is, I have no freedom to choose, because the other fellow is dictated by this relation that we have, which is x2 is equal to 3 minus 2 x1, or x1 is equal to 3 minus x2 by 2. Now if you look at our case where we had the redundancy to come in, this is the problem that we get into, right. This is the problem that we get into, because we could, one of the variables is expressed in terms of the other, and therefore whatever value of x1 you choose, correspondingly there will be a value of x2 which will obey this relation. That is precisely what we had. So how many values that you can choose for x1? You can choose infinitely many values for x1, correspondingly we will get infinitely many values for x2, and that is precisely what we saw as infinitely many solutions. I mean, the third case, let us look at one more. Suppose I had this, what did we do? We said, look, we started with saying 2x1 plus x2 is equal to 3. This was the first example that we studied, and this had one degree of freedom, which means either x1 or x2 we can choose arbitrarily, the other value gets fixed. Now what I do, I write my second constraint which says x1 plus 2 x2 is equal to 3. Now the moment I put my second constraint, there is no way that I will have any degree of freedom. I have lost both degrees of freedom, because there is only one value of x1 and x2 which satisfies both the constraints that is given. So how do we interpret our system of linear equations to the solution and to the constraints? We say that whenever we have a unique solution, that means you have you keep adding the constraints. Now I have added the second constraint, adding the second constraint, in this case the second constraint was nowhere related to the first one, these two are completely different. Having added the second constraint, I see that, look, from the infinitely many values that x1 can take and from the infinitely many values that x2 can take, there is only one pair x1 comma x2 which exactly satisfy these constraints simultaneously. which means whenever we say that we have unique solution, we have no degrees of freedom. Which means if when you have two variables or two unknowns, you add two constraints, there is a chance that you lose both the degrees of freedom, which means you have exactly one point which will satisfy. With this implies, let me do this, implies exactly one point in the plane satisfies both the constraints. So, you can look at the two equations to be two constraints. So, we have both the constraints. It is like saying it is a tightly filled box kind of, right, that is the kind of thing that we are looking at. Now, in the other case that we had, where we took 2x1 plus x2 is equal to 3 and 4x1 plus 2x2 is equal to 6, 2x2 is equal to 6, it was basically a single constraint which is made to look like a second constraint, because the second equation is the multiple of the first. Therefore, we have, in this case, we have 1 degree of freedom. Now, we ask a question. Look, I had two constraints, I ended up getting no degree of freedom, which means there is only one point in the plane which satisfied both the constraints. I had two constraints here, one constraint I hoodwinked to be as the second constraint, I mean I hoodwinked one constraint to be the second, I just took a multiple of the first constraint and then I wrote it as a second constraint. Ultimately, it came down to saying, look, there is only one constraint here and therefore I have 1 degree of freedom. Does that mean if I keep adding constraints, I will end up getting only one point, that means I lose all my degree of freedom, that I get a solution? No, that is exactly what our third example of inconsistency told us. What is that? The inconsistent system where we had 2x1 plus x2 is equal to 3 and the second constraint was 2x1 plus x2 is equal to 8. This fellow is basically, you have two constraints here, but both the constraints can never be met simultaneously. Is that right? That means there is no value of x1 or x2 which lies, I mean which x1 comma x2 which simultaneously solves both the constraints. That is the thing that we have here. So, what we are going to see, if you, what is the other interpretation that we are going to give? We are going to say that, look, even if you add more constraints, it could be so that you may not get a pair of numbers x1 x2 which will satisfy both the constraints. Here the constraints are there, here also we had constraints, here also we had constraints, here also we had constraints. For this set of constraints I could get 1 point, I have lost all my degree of freedom. For this set of constraints I could get infinitely many points, I had 1 degree of freedom, whereas for this guy, for this the constraints can never be met. So, no x1 x2 meets both the constraints simultaneously. Is that clear? So, whenever you have I mean this is something which we need to look at, I mean, or interpret in terms of degrees of freedom. Whenever you have constraints which can be, which are so tight that only one pair, I mean you get, when you have a unique solution, you say that that is the only point which is going to, or that is the only set of x1 x2 which is going to satisfy all the constraints, you have lost all the degrees of freedom. When you have infinitely many solutions, you say that look, okay, I am going to have multiple, though I have multiple constraints here, it all boils down to only one, I will have infinitely many solutions, and there could be a case where the constraints cannot be met at all. It is like saying, okay, I have to be physically present here for recording, and I should also be physically present in another place simultaneously. It cannot happen, therefore I cannot have an x1 comma x2 which satisfies both, and that is exactly we get into the idea of no solutions, right. That is exactly where we get to the idea of no solution. So, having studied all these things, now what we are going to do is, in the next lecture Professor Krishna Kumar will again be dealing with the idea of general system of equations and operations on matrices, the general idea of matrices and operations on matrices. That is what Professor Krishna Kumar will be dealing with in the next lecture, and I will come back again after his lecture to look at, to gain more insights into the topics that we have covered, that are covered by Professor Krishna Kumar. So, in today's class what we did, we basically looked at in the last class of the last lecture by Professor Krishna Kumar, we looked at the idea of the idea of solving system of equations. We didn't per se solve, we looked at geometry of linear system of linear equations in 2 dimension or 3 dimension, and we talked about consistency, inconsistency and stuff, and what we did here is we gave another perspective to the system of equations in terms of degrees of freedom, and we also looked at what would cause an infinitely many solution case and what could cause no solution case and stuff. So, in the next lecture Professor Krishna Kumar will be talking about general system of linear equations followed by matrices, different types of matrices, because we need all these things when we try to solve a system of equations. Till now we have not even been talking about system of equations and solution or solving the system of equations. We are just trying to understand the system of linear equations from a very from multiple perspectives, and this is what we are trying to do. And in the next lecture, as I said, we will look at the structure of general system of equations. We will talk about probably overdetermined, underdetermined systems and stuff, and we will also look at the notions of a matrix. What are the different kind of matrices that you have, followed by various operations on matrices, because you need to do certain operations on matrices in order to arrive at these solutions. So, we need to equip ourselves with what are all the possible operations that you can do on matrices, and that will be the focus of the next lecture by Professor Krishna Kumar, and I will come back again the next day to give you more insights about solving system of the idea of homogeneous system of equations and ideas of matrix operations. We get more insights about these in the lecture after the next lecture. Thank you. Namaste.